Have you ever sat on a train, glanced at the bag next to you, and felt completely still while your friend standing on the platform sees you racing past at full speed? Who's right? Today we're breaking down one of the most fundamental ideas in physics: rest versus motion. Let's start simple. An object is said to be at rest if its position does not change with respect to its surroundings as time passes. If you place a book on a table and walk away, and it's still sitting in the exact same spot when you return, that book was at rest. Look around your own room right now. The walls, the cupboard, the chair in the corner, all of them are at rest with respect to the room itself. Their position hasn't shifted even a little, no matter how long you watch them. Now let's talk about motion. An object is said to be in motion if its position keeps changing with respect to its surroundings as time passes. A cricket ball flying toward the boundary, a fan's blade spinning, a car driving down the street, all of these are in motion. Think about a kite flying in the sky on a windy afternoon. Every second, its position against the clouds and the ground below keeps shifting. That constant shift is exactly what tells us the kite is in motion. Here's where it gets interesting. Imagine you're sitting inside a moving train, and your friend is standing on the platform watching you go by. From your friend's view, you are in motion. Your position relative to the platform keeps changing. But from your own seat, the bag resting beside you hasn't moved an inch. To you, that bag is at rest, even though the train is racing along the tracks. This tells us something important: rest and motion are not fixed properties of an object. They're relative terms. Whether something is at rest or in motion always depends on the reference point you choose to compare it against. There is no such thing as absolute rest or absolute motion in our everyday world. So what exactly is a reference point? It's simply the object or place we choose to measure position against. Choose the platform, and the train passenger is moving. Choose the train compartment, and the passenger's bag is still. The reference point you pick completely changes the answer. To describe motion properly, we need two more ideas: distance and displacement. Distance is the total path length an object covers, no matter how winding that path is. Displacement is the shortest straight line from the starting point to the ending point, along with its direction. Now, motion itself comes in different flavors. First, uniform motion: when an object covers equal distances in equal intervals of time. Picture a car cruising on a highway at a steady 60 km per hour. Check its position every hour, and it will have covered exactly 60 kilometers each time. Next, non-uniform motion: when an object covers unequal distances in equal intervals of time. Think of a bus moving through city traffic, speeding up on open roads, slowing at signals, stopping at bus stops. Its speed keeps changing, so we describe it using average speed instead. Finally, circular motion: when an object moves along a circular path. A stone tied to a string and swung around, or the blades of a rotating fan. Even if the speed stays constant, the direction keeps changing at every single point, which makes this a special category of its own. Let's put a number on motion. Speed equals distance traveled divided by time taken. If a car covers 100 kilometers in 2 hours, its speed is 50 kilometers per hour, meaning its position shifts by 50 kilometers every single hour. And here's the mathematical twist: when there's no shift in position at all, the distance covered is zero, which makes speed come out to zero too. A speed of zero is simply the mathematical face of rest. For non-uniform motion, we calculate average speed instead of a single constant value. Suppose a bus covers 30 kilometers in the first hour, 20 kilometers in the second, and 40 kilometers in the third. Add these up to get 90 kilometers, divide by 3 hours, and the average speed comes out to 30 kilometers per hour. For circular motion, we calculate speed using the circumference of the circle divided by the time period, the time taken to complete one full round. If a stone moves in a circle of radius 2 meters and completes one round in 4 seconds, its speed works out to about 3.14 meters per second. Let's lock this in with a quick recap. Rest means no change in position, motion means continuous change in position, and both are judged relative to a reference point you choose. Motion can be uniform, non-uniform, or circular, and speed, calculated as distance over time, gives us the numbers behind it all.